Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 5 on modeling with linear equations. Linear equations get used all the time in the real world, and so they come up a lot when we're trying to solve problems, especially problems where there's constant rates in them, and we'll kind of be looking at that today. Now, a little heads up, one of the things I am going to be using today for the first time in one of our videos is my TI Inspire calculator. You don't necessarily need a graphing calculator for what we do today, but there is going to be some, let's say, messy number work that we're going to do, and I just want to have that here so I don't have to do some long division by hand using decimals. I don't really want to do that. So I'll be pulling up my TI Inspire calculator on occasion today. For most of the problems, we won't need it. The most you really need is like a little handheld scientific, but if you've got your graphing calculator with you today, there's no reason not to break that out and get a little bit of work with it. All right, so let's jump right into it and start to do a little bit of modeling. Now, modeling real world scenarios. Now, when we model real world scenarios with linear equations, it takes practice. But the following steps can help with the modeling process. So let's take a look at Weiler's steps for the modeling process. One, and this is important, clearly define the quantities involved with common sense variables and let statements, okay? That is really, really critical to really understand what quantity your variables represent. 2, pay attention to the units in the problem and use them to help you model the situation. You should feel comfortable with units of length and area and time and weight, right? And all of those will come up here and there in these types of problems. 3, use your let statements to write expressions for quantities you're interested in. Notice I said, expressions, right? Not necessarily equations, but expressions. 4, carefully translate the information you're told into an equation with the help of units, right? And those expressions you've written. Solve the equation. Remember to mentally note the justification you're using for each step so that you know that you're doing it correctly. And finally, check the reasonableness of your answer. Does it make sense, right? If I'm solving, let's say, for the price of an object, a gallon of milk, and I got $22 for a gallon of milk, something is wrong, Or if I'm solving for a person's age and I get a negative number, something is wrong. That's not a reasonable answer, all right? So we should always reflect on our mathematics. We shouldn't just get an answer and be like, I'm done and moving on, okay? Math is about making sense of things. So if your answers don't make any sense, then possibly your math doesn't either. All right, let's get into some modeling with exercise number 1. Keyshawn is modeling the amount of money he has left at a theme park where rides cost $4.50 each. He started the day with $65, and after taking a certain number of rides, he has $29 left. He is trying to algebraically determine the number of rides he has taken if he only spent money on rides. Great. Well, kind of going through that modeling process, letter A, what would be a good choice of variable for the number of rides that Keyshawn has taken and why? All right, well, pause the video now and you choose a variable, right, for the number of rides that Keyshawn has taken and tell me why you think it's a good choice of variable. Pause the video now. Well, I think that there's many different good choices. Some people just default to X. And the reason for that is that they're comfortable with the variable. They just, X is the most common variable used in mathematics. We've seen that already. So a lot of people will go with that. But I think that the two that make the most sense is either using N for the number of rides or using R because that's what, the word rides starts with. So I'm going to go with R, okay? A little non-standard. I'm going to let R be equal to the number of rides. And that's the reason I'm choosing it, because the word rides begins with R. Awesome. Let's take a look at letter B. Give an expression, just an expression, involving your variable from A for the amount of money that Keyshawn has spent on rides. Okay? I just want to know, right, if he took R rides or N rides or whatever variable you used, each one of them costs $4.50 each, right? Then just give me an expression for how much Keyshawn spent on rides. Pause the video now. Well, look, this comes up all the time. And what do I mean by this? What I mean by this is when you have the price, what's called a unit cost, right? The price per something, right? The price per ride, the price per gallon of gas, the price per brownie, whatever you have, right? And then you have the variable standing for the number of those things. Well, how much you spent on them then is simply that unit cost, 450, times the variable. So it's 4.50 times r, or 4.50 times n, or 4.50 times x. Now, by the way, we don't really need the zero. Let me make that decimal point a little bit bigger so you can maybe see it on your screen. Right? We don't absolutely need the zero. We could have 4.5 times r. I hope everyone is comfortable that 4.5 and 4.50 are the same number. But because we're talking about money, I think I'm going to keep that zero. All right, let's look at letter C now. Using B and the information given in the problem, create an equation that represents this situation and solve it to determine how many rides Keyshawn took when he had $29 left. All right, well, I'd like you to look back at all the information that we're given, and we really need to bring that information back, right? All the information that's given, and I'd like you to try to model the situation simply with an equation. All right, then we'll come back, talk about the equation, and then we'll go on to try to solve it. Pause the video now and see if you can come up with an equation that models everything that they told us here in this problem. Well, let's state the obvious, right? If we take the amount of money that Keyshawn started with, and we subtract off how much he spent on rides, that should then be equal to how much money he's got left. Well, how much money he started with, which is $65, minus how much he spent on rides, which is $4.50 per ride, should be equal to how much money he's got left, which is $29. So there's our equation. That models absolutely everything that's been given to us in this problem, right? $65 minus $4.50 times the number of rides he took is equal to the amount of money that he has left. It's this 450 here that's going to necessitate that I use the calculator. All right, what I'd like you to do is pause the video now, solve this equation, and see how many rides Keyshawn took. All right, well, I don't know if you need to do this, but I always like to do it in these problems. I'm going to flip-flop using the commutative property of addition. I'm going to rewrite that first line as negative 450r plus 65 is equal to 29. I'm going to subtract 65 from both sides. That's going to give me negative 450r. Hey, why not bring the calculator out right now? I've got 29 minus 65, just trying to find a spot for it. 29 minus 65 is going to give me a nice negative number, hopefully. Hey, nothing's working here. Let's try that again. Maybe that's... There we go. I had to get my calculator there. 29 minus 65, that's a little bit better, equals negative 36. Now I can move my calculator a little bit this way, and then I'm just going to divide both sides by negative 4.50 divided by negative 4.50. Those cancel. Let's just hit the divide button. Negative 4.50, enter, and it looks like Keyshawn took 8 rides. All right, let's put you back away for a little bit. All right, so Keyshawn took 8 rides. All right, simple enough. And again, we don't absolutely have to have the calculator, but it's going to be a little bit difficult to divide 36 by 4.50, just kind of in our heads. Let's take a look at letter D. Later in the day, Keyshawn notices that he now has only $10 left. Is it possible that Keyshawn has only spent money on rides? If so, how many? If not, why not? All right, great. Well, what I'd like you to do is play around with letter D, model the information given, based on what we have and based on the assumption that Keyshawn is only taking rides, right? And see what you find. Pause the video now. All right, well, very similar to before, right? If Keyshawn was only taking rides, then 65 minus 4.50 times the number of rides he took would have to be equal to 10. So I'm going to subtract 65 from both sides. This time I think I'm going to just do that subtraction in my head. I get negative 4.50 times the number of rides he took is equal to negative 55. Divide by both sides by negative 4.50 and negative 4.50. Cancel. Right, and now let me bring my TI Inspire back up, or maybe not, lose it entirely. I'm going to have negative 55 divided by negative 4.50, enter, and that gives me R equals 12.2 repeated. Okay, so how do we interpret this? R equals negative 12.2 repeated. Well, it tells me that, right, if Keyshawn took only rides, then he would have to have ridden exactly 12.22222 rides, right, in order to get it down to $10. And so what that tells me then is he couldn't have only taken rides, right? So he couldn't have only spent money on rides because he can't take a fraction of a ride, right? There's just no way. There's no way for him to actually take 12.2 rides. I mean, forget about the fact that the 2 is repeating forever. Even if the answer had just been 12.2, that's not possible. All right, let's do a little more modeling. Now, there are lots and lots of different situations that can be modeled with linear equations, and we're going to spend another lesson on it in the next lesson. But when we're dealing with trickier modeling, it's often helpful to work through numerical examples at first to understand how all the variables relate to each other, right? And it's only once we understand those with sort of numerical examples that we then want to go with the algebraic. So let's take a look at exercise number 2 and an age problem. Age problems can be particularly tricky for kids. Let's take a look. Evie and her father are comparing their ages. At the current time, Evie's father is 36 years older than she is. 3 years from now, Evie's father will be 5 times her age at that point. How old is Evie now? All right, so we have these 2 pieces of information. One of them is that at the current time, Evie's father is 36 years older than she is. Now, if you're thinking, wait a second, no matter how many years go by, he's still going to be 36 years older than her. That is actually true, all right? But let's roll with it. In 3 years, right, Evie's father will be 5 times her age, all right? Somehow we can use those 2 pieces of information to figure out how old Evie is. Let's take a look at letter A. It's helpful to try to solve this problem by guessing and checking, just to make sure you understand how all of the ages relate to one another. Fill in the table below with some possible ages for Evie. All right, so for instance, let's say Evie's quite young, right? Let's say Evie is 3 years old. Well, we know Evie's father is 36 years older than her, so that would be 3 plus 36, and that would be 39, right? So we would know that those were their 2 ages. Now, how old is Evie in 3 years? Well, that's easy enough. That's going to be 3 plus 3, and that's going to be 6 years old. And how old is Evie's father in 3 years? Well, that's going to be 39 plus 3, and that's going to be 42. Okay? The question now is Evie's father's age 5 times Evie's age, right? Well, we could just do 5 times Evie's age, right? And that's that after 3 years. And that's 30, which doesn't equal 42, so that's no, right? So Evie's age in 3 years, which was 6 years old, you know, if we do 5 times that, we don't get up to her father's age because we know that would have to be 42. So Evie's current age is not 3 years old. What I'd like you to do is pause the video now and do 2 more of these and see if you can find the right one. If you can, that's cool. We're still going to do it algebraically, but if you stumble on the right one, awesome. All right, well, let me go with another one that's relatively young. Maybe then we'll go with an older one. Who knows? Maybe Evie is an adult already. So let me go with Evie being 5. If Evie is 5, then her father is 36 years older. Her father is 41. In 3 years, Evie would be 5 plus 3. She'd be 8. Her father would be 41 plus 3. He'd be 44, right? If we do 5 times Evie's age, 5 times 8, we'd get 40. And that's relatively close, but it's not 44, right? Remember, 5 times Evie's age would be equal to her father's age, and father's 44, but 5 times her age would be 40, so nope. Let me go with a much older one. Let me go with Evie's 10, right? So let's say Evie is 10, right? Her father would be 10 plus 36, he'd be 46. In 3 years, Evie would be 10 plus 3, and that would be 13. In 3 years, her father would be 46 plus 3, which would be 49. Man, that's old. And then let's see if we do 5 times 13, we'd get 65, which is definitely not equal to 49. So Evie is not 10 either, right? She wasn't 3, she wasn't 5, she wasn't 10. But the great thing about going through this process is that all is giving us a feel for how we do the algebra. So let's take a look. Letter B. Set up an equation that represents the information given in the problem based on Evie's current age. Carefully define quantities for her father's current age and the ages in 3 years. Solve the equation you create to determine Evie's current age. All right, great. Let's choose the most obvious thing ever. Let's let E be Evie's current age. Here we go. Let E equal, maybe I should capitalize her name, Evie's current age. All right, so that's going to set the basis for everything, right? Then I'm going to say E plus 36 be Evie's father's current age. All right, now in 3 years, right? In 3 years, let's talk about what we got. Well, Evie is going to be E plus 3, obviously, and E plus 36 plus 3 will be the father's age. All right, I'm going to move out of the way in just a second. We're going to take a look at all of this. All right, so no equation yet. I'm not worried about an equation. Evie's current age. We know her father is 36 years older than her. That's E plus 36. In 3 years, obviously, Evie's age will be E plus 3, and Evie's father's age will be that E plus 36 plus another 3, right? Simple enough. Now we have to model, though, the information that says in 3 years, Evie's father will be 5 times Evie's age. Now think about how easy that is, right? Evie's father's age will be 5 times Evie's age. That's what we're told. So let's put that equation right here. Evie's father's age, which is E plus 36 plus 3, will be 5 times Evie's age. All I'm doing is directly translating that final statement In 3 years, Evie's father's age, which is E plus 36 plus 3, will be equal to 5 times Evie's age. And of course, I need to have that E plus 3 in parentheses because I need to multiply Evie's entire age in 3 years by 5, not just the E. Of course, solving this is pretty easy at this point, right? I can remove the parentheses and I can use the associative property of addition on the left-hand side to say E plus 39. On the right-hand side, I can use the distributive property to multiply through by that 5. I could now subtract an E from both sides. Give myself a little bit of room, move my calculator out of the way. Right? I will now have 39 is equal to 4E plus 15. Subtract a 15 from both sides. Right? Now I'll have 24 is equal to 4E. Divide both sides by 4. And Evie must be 6 years old. All right? And that's it. By the way, notice that wasn't one of the ones that I had up here. Right? Had I done like, one more line, but with E equals 6, I would have gotten or would have seen that it was right. And I bet that there were some of you out there that did do 6 as a choice for Evie's age in this table. And hopefully you found, oh, yeah, that checks when I work it all out. But ultimately, I can use all the information that I'm given to model this particular equation to the problem, and then I can solve it to figure out what Evie's age is. It's that easy. All right. Yeah, Evie's current age. Got it. Let's do one more problem. Exercise number 3. Kirk has $12 less than Jim. Unlikely, but maybe. Kirk has $12 less than Jim. If Jim spends half of his money and Kirk spends none, then Kirk will have $2 more than Jim. Letter A. Choose an appropriate variable to represent the amount of money Jim initially has. Then also write an expression for how much money Kirk initially has in terms of this variable. All right, this should be easy enough. Why don't you pause the video and go ahead and write down those let statements for A. All right, should be simple enough, right? I think I'm gonna let J be the amount Jim initially has. All right, and I'm gonna let J minus 12 be equal to the amount Kirk initially has. And we'll make that N into a blue. All right, great, right? This is the amount that Jim initially has. J minus 12 is the amount that Kirk initially has. And of course, it's J minus 12 because Kirk has $12 less than Jim. $12 less than Jim. Now for the hard part. Set up an equation that represents the situation described after Jim spends half his money. Solve the equation to determine how much money Jim initially had. Okay, so let's go back, right? Take a look. Kirk has $12 less than Jim. That's really just wrapped up in this let statement right here. If Jim spends half of his money, now think about that. If Jim spends half of his money, what he has left is 1/2 times J, or J divided by 2, really, right? But when he spends half his money and Kirk spends none, then Kirk will have $2 more than Jim. The amount of money Kirk has will be $2 more than the amount of money Jim has. Pause the video now and see if you can model that and solve your equation to find out how much money Jim initially had. All right, well, one thing that's very important to understand is that after Jim spends half, he has 1/2 times J left. All right, or j divided by 2. Now this would be different if he spent a quarter of his money. Then he'd have 3/4 times j left. But after he spends half his money, he has 1/2 times j dollars left. And what we know is that at that point, Kirk has $2 more than Jim. All right, well that's easy enough to model, right? If I take the amount of money that Kirk has, which is j minus 12, that would equal the amount of money that Jim has, which is 1/2 times j, plus another 2, right? The amount of money that Kirk has, which is j minus 12, right, because he didn't spend any money wisely, right, is going to be 1/2 times j, which is the amount of money Jim has after he spent half his money, plus an extra $2. How do I solve that? Well, the first thing I might want to do is I might want to add 12 to both sides. That will give me j is equal to 1/2 times j plus 14. I could then subtract 1/2 j from both sides. Now I know fractions are nobody's favorite, but if I have j minus 1/2 j, that's going to give me 1/2 j is equal to 14. I can now multiply by 2 on both sides. And it looks like Jim originally had $28. Right? Now, you can really check this one, right? It said initially, right, Kirk had $12 less than Jim, right? So in this case, Kirk would have 28 minus 12 would have 16, right? And then it said, well, if Jim spent half his money, right, so half of 28 is 14, so if he spent half his money, he'd still have half left, it'd be 14, right? And at that point, Kirk would have $2 more than Jim. Well, if Jim had 14 and Kirk has 16, then in fact, Kirk has $2 more than Jim. So that's it, right? Jim initially had $28. But we have to be very, very careful about our let statements, what's going on, how they relate, right, to each other after the money's been spent, and all of that. And that can be a little bit tricky. So you're going to definitely get some practice on things like that and thinking like that on the homework. So let's wrap it up. All right, so nothing new in this particular lesson in terms of solving problems, right? The algebra that we were doing was actually algebra that we had learned and we had reviewed throughout this unit. What was new, of course, if anything, was actually spending the time setting up let statements and modeling the information that we were given in a particular problem using an algebraic equation. The actual solving of the equations, I hope, were not all that difficult. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.